This is a summarization of what we just looked at with our examples. We're looking at rational functions. The degree in the numerator is going to be our m. The degree in the denominator is going to be our n. Just so that you'll know what these rules are talking about to begin with. So if the degree in the numerator is less than the degree in the denominator, that would be something of this sort. So we'll call this a bottom-heavy function. So if I have a bottom-heavy function, that would look like some x squared over x to the third, or x squared over x to the fifth, something where the denominator had the higher power. Then what they say here is that the denominator kind of determines what happens to this function in the end. In which case, if it's a bottom-heavy function, so I'll write it like this, a bottom-heavy function, that means y equals 0 is your horizontal asymptote, because the bottom overtakes this function in the end, or in the tails, if you will. B, we'll call this an evenly balanced function. So on this evenly balanced, because the degree in the numerator is the same as the degree in the denominator. So in our evenly balanced function, that would be like some 2x squared over 3x squared, and it would be plus blah 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 plus blah 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 plus blah 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 plus blah blah blah, and it can have other things in there with it, but we're looking at the highest powers. That's what this m and n refer to, just the highest powers. If it's evenly balanced, then what you would do is you take the ratio of these coefficients, because in the end, whatever your number is, if it's 1,000,000 squared over 1,000,000 squared, those millions cancel out, leaving you with just that ratio of the coefficients. So I will say evenly balanced, y equal ratio of coefficients is horizontal asymptote. The C case is for a top-heavy function. On this top-heavy function, we've got something that is like some sort of x cubed plus blah blah blah, and it can have a 2 or 3, doesn't matter, over the degree in the numerator is heavier or bigger than the degree in the denominator, so we'll just say that this is a 3x squared plus blah blah blah, looking at the highest powers there. When this happens, the degree in the numerator overpowers that of the denominator, meaning that it's going to shoot up to infinity or negative infinity, depending on how the negatives and the powers play out. So this has no horizontal asymptote. Then in the D section, this is going to refer to a slant asymptote, which we will get to in the very next discussion. So this means, now that remember that the m, so I'll call this the slanty guy. This means that the degree in the numerator is one less than the degree in the denominator. So it would be like some sort of x squared over x cubed. So the degree in the numerator is 1 less than the degree in the denominator, and we're going to come up with a way to find that. I'll just say we'll need to find equation of slant, and we'll do that in the next one. And then the last part in the tails, if we are in P and Q, this is just talking about the vertical asymptotes happening in the denominator if they have no common factors. So check for vertical asymptotes where denominator equals 0. So you'll look at those factors and figure out where that denominator can be equal 0, provided no common factors, meaning that nothing factored out. If it did factor out, what you would have is a hole and not a vertical asymptote there, and we looked at some examples of this as well in the earlier section. We already looked at these functions in the previous video, the part A, but I would like to look at it using our rules so that I don't have to do that formal finding the limit in order to determine the end behavior of these functions. If I observe this function, I notice that he is bottom heavy. Since he's bottom heavy, y equals 0 is a horizontal asymptote. I believe that was what we found. So y equals 0 is horizontal asymptote. I could say the limit as x goes to infinity or negative infinity, depending on whatever it is that I choose. Both of them are going to 0. This b part, and I've already looked at the graph these and confirmed it, so I won't do that again. For this b part, I notice that it is evenly balanced. I have an x to the fourth, and so I'm going to take the ratio of those coefficients and say that y equal 40 over 10, which is 4, is my horizontal asymptote. This means I could write the limit as x goes to infinity of this g of x is 4. The next one is top heavy, so I'm going to write even. Write that this one is top heavy, so it follows part C, no horizontal asymptote, which means that it's either going to positive infinity or negative infinity, which is what we found. We're going to be looking at these slant asymptotes, figure out what's going on with them, and I'm going to show you how to determine what the equation of that slant asymptote is. I'm sure you've gathered by now that what we want to know is the limit as x goes to infinity, and both positive infinity and negative infinity of this particular f of x. And I need to get it out of this form so that what I'm trying to do is figure out what's going on here with this slant asymptote, and how do I get that equation. If you'll go ahead and divide this out, remember, reach way back into the depths of your algebra training, and let's do long division. If you remember your synthetic, you can do that as well. I'm just going to start here, and x goes into 2x squared 2x times, so just as in regular division, I'm going to multiply 2x squared plus 2x. Just as in regular long division, I'm then going to subtract. Remember that you have to subtract each term. Chink, ka-chink. Then I will add. You're gone. You're a 4x. Bring down your minus 2. X goes into 4x plus 4 times. Multiply 4x plus 4. Then I'll subtract. Then I'll add again, just as I do in regular division, minus 6. What I have left, because I've done this division, is limit as x goes to infinity of 2x plus 4, and then minus still this 6 over x plus 1. What is going on is, as I'm looking at this function f of x, which is 2x plus 4, minus 6 over x plus 1. In the tails, this function is approaching this 2x plus 4, while this term is going to 0. So that's how they got that 2x plus 4. And that is the equation of the slant asymptote. So if you're asked for the equation of the slant asymptote, that would be this 2x plus 4. And that is where this equation is going in the tails. Lastly, we're going to look at the end behavior of some transcendental functions. First up, we have the graph of e to the x. So we're going to look at, and they want us to do it for both e to the x and e to the negative x. So I just have the graph up of e to the x, and then I'll just draw e to the negative x. The limit as x goes to infinity of e to the x. I look to see what happens as x gets larger and larger. This thing is shooting up to infinity. The limit as x goes to negative infinity of e to the x is as x goes closer and closer to negative infinity, this thing is getting closer and closer to the x-axis. In other words, it's going to y equals 0. Next, let's do limit as x goes to infinity of e to the minus x, which is the same thing as saying limit as x goes to infinity of 1 over e to the x. If e to the x is going to infinity, this thing would be going to 0, and the limit as x goes to negative infinity of 1 over e to the x. If e to the x is going to 0, this thing is going to infinity. Next, I'm looking at the natural log of x. They want to remind you that natural log of x is the inverse of e to the x. This one is a little bit different. We can look at the graph of natural log of x, which is the blue. So I'm going to look at limit as x goes to infinity of natural log of x. This function is getting larger and larger slowly, but it is getting there, so it will go on to infinity. But now, because of the way the natural log is defined, he doesn't go to negative infinity. His domain just goes to almost 0. So I can just go do the limit. His end behavior would just be as x goes to 0 from the right, because he doesn't exist over there to the left, of the natural log of x. And this would be as it gets closer and closer to 0 from the right, this thing is going to negative infinity. Another one that's a little different, let's look at the limit as x goes to infinity of cosine x. I see that as x gets larger and larger, the cosine just continues to oscillate, and it's not going to any one value, it's not going to infinity, it's not going to a number, so this limit does not exist. And same for the negative end. The limit as x goes to negative infinity of cosine x does not exist. Oops. Alright, and that concludes part B. Remember, if you are having any questions or you need any help with anything, please come to the Blackboard Collaborate or email me.